Here's your answer key for the 2.2 practice assignment. It's a really good idea to have your 2.2 reading out while you are doing these worksheets. For example, in section A, you're going to need that because all of the vocab words you need to fill in the blank come directly from the side of your 2.2 reading. Starting out, an object's position is a property that describes where it is compared to another object. We represent that with the variable x in all of our formulas. Number two, displacement is a property that tells us how far an object is from where it started. Number three, anytime we want to communicate that an object has changed, we use a delta symbol. So remember, the delta is the little symbol that looks like a triangle, and we will use that anytime something changes. If x is position, then delta x will be our change in position. The total length of a path an object moves is the distance. And last, east and west are each examples of direction. In section B, I'm having you review some of the graphs from the 1.2 reading, sharing data in science. You're going to need that to find these answers. The type of graph that is best for showing change over time is a line graph. Number two, what graph is useful for comparing categories? The key word here is categories, and we can see that in the reading, bar graphs are useful for comparing values for different categories. If I mention categories, I'm talking about things that can be more easily named than measured, like cities. If I mention properties, then that is going to be better for a scatter plot. So number three, what type of graph will work best for comparing how the mass of different candles affect how bright they burn? Well, the mass of a candle is a property we can measure. The brightness of a candle is a property we can measure. So therefore, the best graph here is going to be a scatter plot. Answers for number four will vary a lot. For number three, you need to choose which blank you need to write distance and displacement. The total distance is always all of the paths that an object took. So if we're starting at x sub 1, the distance is going to be all the way 6 meters right plus another 3 meters to the left. So this green line would be the total distance. Our displacement is just how far we are from where we started. If we started at x sub 1 and we ended at x sub 2, then our displacement is just the separation between those 2 points. So then decide which one is the distance and which one is the displacement. On the second page, you need to know that all of your answers need to be written with the correct unit, otherwise they are not correct. So a dog is 5 meters to the left of the fire hydrant. After a few seconds, the dog is 2 meters to the right of the fire hydrant. So I need to label the arrows with x sub 1 and x sub 2. X is the variable that represents our position. So x sub 1 is our first position, or where we start. The dog starts 5 meters to the left of the fire hydrant. So the arrow that is 1, 2, 3, 4, 5 meters to the left will label as x sub 1. And then its ending spot is 2 meters to the right, so we'll label that as x sub 2. Over here, we can write in the value for x sub 1 as negative 5 meters. Remember, it's got to be a lowercase m. X sub 2 is at 2 meters, so we'll write 2 lowercase m. You can also write out the word meters. Either way is totally fine. The formula for displacement is delta x is equal to x sub 2 minus x sub 1. So if I use this formula to calculate, then delta x, or my change in position, should be equal to x sub 2, which was 2 meters, minus whatever x sub 1 is. In this case, it's negative 5 meters. So my delta x is equal to negative 2 meters minus negative 5 meters. 2 minus negative 5 will give me a total of 7, so my displacement was 7 meters. To double check your answer, just count it up on the number line. I should be 7 meters in the positive direction from x sub 1 to x sub 2. 1, 2, 3, 4, 5, 6, 7. So my delta x was 7 meters in the positive direction. Problem number 2. The fire hydrant is defined as 0 meters and also x sub 1, so I'm just going to go ahead and label that right away. The dog then moves to a position 4 meters to the left. 4 meters to the left is going to be 1, 2, 3, 4. Nope, I don't know my right and left. To the left, 1, 2, 3, 4. So over here is x sub 2. Again, I'm going to use the formula delta x is equal to x sub 2, in this case, negative 4, minus x sub 1, which in this case is 0 meters. So all I have to do to find out my answer is negative 4 minus 0. It makes sense that we have a negative answer here because our change in position was in the negative direction. Be sure your answer has a unit. Number 3 is a little bit different in that it is asking you to find both the distance and the displacement. To do that, let's first label x sub 1 for the dog. That's at negative 1 meter. We don't know what x sub 2 is, so we have to follow the directions to figure out where it was going and where it ended up. First, it walks 2 meters to the right, 1, 2. Then it walks 5 meters to the left, 1, 2, 3, 4, 5. So in this case, now we know that it ended up at negative 4 meters. So we'll label that as x sub 2. To figure out the distance, we need to know the total path that it traveled. The total path it traveled was 2 meters right and then 5 meters left. So our distance is going to be 7 meters. If we're talking about distance, it doesn't matter if it was positive or negative. No matter what the direction was, we just add up the total number of meters. The displacement is a little bit different because it is just the separation between your starting point and your ending point. So when we're finding displacement, we're at x sub 1 and moving to x sub 2. Use your formula the same way you did on the previous problems to solve this question. Remember, include your units. For number 1, I'm going to say that anywhere behind the starting line is negative and anywhere in front of the starting line is positive. That means if the car is behind the starting line to start, x sub 1 is going to be negative 5 meters and x sub 2 is going to be positive 10 meters. After we've defined x sub 1 and x sub 2, all you need to do is place those into your formula, but it doesn't really matter if down is positive or negative. While I don't define anywhere as positive or negative here, I think it makes most sense to count down as the negative direction. So we'll say x sub 2 is equal negative 5 meters. Then, once again, use the formula to calculate the correct answer. Don't forget your units. For number 3, it makes the most sense to say that below ground is negative and above ground is positive. So if a squirrel is starting 2 meters below the ground, then we'll say x sub 1 is equal to negative 2 meters. Then they run up to the surface and then run up a tree until they are 3 meters above the ground. So we'll say x sub 2 is equal to 3 meters. Again, use delta x is equal to x sub 2 minus x sub 1 to find the total displacement. In number 4, we have a student running in multiple directions, and we need to find both the distance and the displacement. In part A, we find the distance. All you need to do to find distance is add up distances that they ran. 4 meters to the right and 8 meters to the left added together will tell you the total distance. And remember, distance does not take direction into account, so you can just add those numbers together without worrying which is positive and which is negative. To calculate the displacement in part B, it helps to draw out a number line. X sub 1 we know is at 0 meters. They run 4 meters to the right, and then they turn around and run 8 meters to the left. So if we had to go 1, 2, 3, 4 to the right, then running to the left, we go 8 meters. 1, 2, 3, 4, 5, 6, 7, 8. That will put x sub 2 at negative 8 meters. It helps to write down the values of your different variables before calculating. So I like to write down x sub 1 equals 0 meters. x sub 2 equals negative 8 meters. And after that, you have everything you need to plug those numbers into your delta x equals x sub 2 minus x sub 1, and then you'll have the displacement.